Alright, hi everyone, this is the second video on the introduction to chapter 4, electric potential, and we are going to talk in this video about what is the electric potential. We've seen in the previous video that we could define the electric potential energy using the work formula and integrating over all the displacement, and we came up with a formula that defined the total energy needed to bring a charge from infinity to a certain distance r. So just as a reminder from last video, the change in potential energy is equal to the Coulomb force multiplied by the 2 charge, and we have 1 divided by rb. Now note the value b here is the final point at which the charge stop. The value RA is the distance, the initial distance. All right, so that's important. And again, we will be solving many examples. It will become more obvious in the coming video. All right. Now, just like we did in chapter 2, we created the analogy between the electric force, the Coulomb force, versus the electric field. So the electric field was derived to simplify some of the calculation without having to worry about the test charge. Well, the electric potential followed the exact same logic. It even involved the electric field. So the electric potential is to give us an idea of, to easily calculate the electric potential energy at different points in space without knowing in advance what will be the total charge that is going to be moving in that space. So basically, the electric potential used the letter V, V for voltage. Now, by the way, you probably heard about the term voltage before. I first studied in electronic and I'm used to saying voltage instead of electric potential. So if you hear voltage, it means electric potential. So the electric potential or voltage is equal to the electric potential energy divided by the extra charge. So in this case, I divided by Q2, which was our charge that we were moving. So it is equal to the Coulomb force, Coulomb constant, sorry, multiplied by the first charge divided by the radius. So note, since we are using the electric potential energy and we're simply dividing by constant, that means we don't have to redo all the integral and derivation that we did in the previous video. The result will be the same, except that Q2 has been removed. Okay, we can do this because Q2 is a constant, is considered to be a constant, even though we don't know in advance what it's going to be. If we want to calculate the change in potential in electric potential, the change in voltage, we use the same logic we did with the change in electric potential energy. So it's the same formula basically, except that we remove Q2. All right. Now note, the electric potential is in volt. I'm not sure if I mentioned it in the previous video, but the electric potential energy is in joule. All right, so it's a form of energy. It's always defined in joule. The voltage is in volt, and basically, if we want to find out what is the amount of energy to bring a charge against a certain voltage, we simply multiply the charge by the voltage and we get back into the unit of joule. All right. Talking of this conversion, we are going to introduce a new value, the electron volt. So often, not as often in this course, but you will see in your third semester, we will often use a value called the electron volt. So let's imagine, for example, that we have a charge that is fixed in place and it creates an electric potential around itself. And let's say the electric potential from infinity to a distance of 1 meter next to it is 1 volt. Well, if we were to take an electron from infinity and bring it at 1 meter or against 1 volt, it will require an energy of 1 electron volt. In other words, the charge of the electron multiplied by 1 volt. Recall, the charge of the electron is 1.6 multiplied by 10 power minus 19 Coulomb. Therefore, 1 electron volt is equal to 1.6 multiplied by 10 power minus 19 joule. All right? So this value will pop up here and there in this semester, and you will see it often in your third semester. Last concept before we move on to solving some example is the principle of superposition still apply here. So if you want to calculate the voltage at a certain point in space and you have multiple point charge, not just one. Well, what you can do is calculate the voltage from infinity to a certain point from one of the charge, then add the voltage from infinity to the same point of the second charge, and so on and so forth. Now, don't freak out if you're not sure what I'm talking about here. This one, again, is way easier to see when solving an example, and that's exactly what we are going to do in the next video. All right, so see you in the next video.